of Miami. And today he will talk to us about solving a black hole spin chain. Please, Rafa.
Thank you, Anna. So thank you to all the organizers for the invitation. An apology that I'm not exactly on the topic, but I think I'm not the only guilty one here. So yes, the title is Solving a Black Hole Spin Chain. And the outline is very straightforward. I'll begin with a brief introduction, and then I'll describe a model and the solution to the model, and then a few bonus results that came out of solving this model, and then finally a brief outlook. And I should emphasize that this is joint work with Anna, the host, and this is appears in a pair of papers from this year. Okay, so let's begin with an introduction. So late last year, there was a very interesting paper by Robertson, Jacobson, and Soler, which focused on a very interesting open spin chain. And of course, spin chain is integrable, otherwise I wouldn't be talking about it here. And one of the remarkable features of this spin chain is that its continuum limit is a non-compact CFT. So that means that it has a continuum of conformal dimensions, even though it's a lattice model with a finite number of degrees of freedom at each site. And this work, which was for the open spin chain, builds on previous work for periodic spin chains mentioned here. And this spin chain is related to so-called Euclidean black hole sigma model, which has a very long history, dating back at least to Within, 1991, and many other luminaries. So for this reason, and just to make it sound fancy, I decided to call this the black hole spin chain. And that's what I'll be talking about today. So of course, since the model is integrable, then we expect to have an exact solution. And the question is, what is it? Well, actually, a few years ago, we conjectured a partial solution to this model. And then based in part on that conjecture, then in the same paper, the authors conjectured a full solution to the model. But still, this solution wasn't proved. And so the aim of this talk is to present the proof here. And it won't be a technical talk. And what I want to emphasize is the key idea of the proof. And that's something we call a factorization identity, which I hope you'll find interesting. Okay, so let me say, tell you what the model is. So as I already mentioned, this black hole spin chain is an integrable open chain. So as Sklyanin explained a long time ago, an integrable open spin chain is constructed from two basic building blocks. So one of them is the R matrix, which is, of course, a solution of the Yang-Baxter equation, which you'll recognize. Now, I've written the R matrix in a very Baroque way with this blackboard font and a tilde. So sorry about that, but I think it's useful, but it'll be clear in a few minutes why we have this notation. So please be patient, and I hope it'll become clear. And then in addition, another basic building block is the so-called K matrix, this guy here. So again, I use this Baroque notation, blackboard font and with a tilde. And it satisfies the boundary and Baxter equation written here. And there's actually two of them, a right and a left. So this is the right, and that's why we put this extra superscript R. Okay, so given these building blocks, one can then construct an open spin chain transfer matrix. Now, in today's talk, we're going to focus on an R matrix associated to D22. So the twisted D2R matrix. Now, you probably haven't heard too much about this R matrix. I'll just say a little bit about it. It's at each site, the vector space is 4-dimensional. So this is a 16 by 16 R matrix. Of course, it's trigonometric, so it has some anisotropy parameter, which we'll call eta. And well, this guy, as well as many others, were written down a long time ago by Bajanov and Jimbo. But among the infinite families of trigonometric R matrices, this twisted Ds are the most complicated, which is probably why you haven't heard a lot about them. And so indeed, there's not too much known about such models. Coming back to the K matrix, so since we have at each site 4-dimensional vector space, the K matrix here is 4 by 4. And again, it'll depend on the same anisotropy parameter. I'm not going to write down explicit formulas for either R or K, but you can look at the papers and you'll find them. Well, I should also say that this K matrix also depends on some discrete parameter, epsilon. It can have either value 0 or 1, and we're going to focus on the case epsilon is 1. So this is a one that corresponds to this black hole spin chain. Yes, and these K matrices were discussed already before. And then, so following the recipe of Sklianin, then the transfer matrix for the model is written like here. Again, everything here is blackboard font, and so also the transfer matrix is this blackboard T, and everything also has a tilde. So, so these guys here, the monodromy matrix is just the product of n copies of the R matrix. And then, and this guy here with a hat is again n copies of the R matrix, but now written in the reverse order, and also the indices are permuted, right? Instead of 0 n, we have n0. So KR, I already told you about before, and then this K left is related. So this is a left K matrix, so related to the right one in a simple way, and this M is some simple diagonal matrix. Okay, so now this transfer matrix is defined. And one of the nice features of this transfer matrix is, and therefore all the conserved quantities of the model, is that it has a quantum group symmetry. I'll call it UQB1. So what that means is that the transfer matrix commutes with the n-fold coproduct of diagonal generators, H tilde, and also the raising and lowering operators, E plus and E minus. And just to be a little bit more concrete, so at one site, this H looks like this, and these E plus looks like that, and E minus is just the transpose. And then to go to more than one site, we used a coproduct. And these are just familiar coproducts from quantum group symmetry. And then again, these guys obey the usual quantum group relation. And as before, eta is the anisotropy parameter. So all this is just to tell you that it has some familiar quantum group symmetry. Okay, so that's the model, and now we like to know how to solve it. So of course, by construction, the transfer matrix commutes for different values of the spectral parameter. So that's what the hallmark of integrability. How to solve. So in particular, we would like to know the eigenvectors and the eigenvalues of the transfer matrix. And as I mentioned at the introduction, the key idea that we used is something we call the factorization identity. And at the most fundamental level, this factorization identity just boils down to the fact that if you consider the SO4 Lie algebra, it's just two copies of SU2 Lie algebra. So this is something which is probably very familiar, but in case you forgot how that works, let me just briefly remind you. So we know that the SO4 Lie algebra, the generators are just antisymmetric 4x4 matrices. So we can write them as MAB, where A, B go from 1 to 4, and EAB here are just the elementary matrices, which are everywhere 0 except for 1, 1. So these are obviously antisymmetric. And then what you do is you pick out 3 of these guys this way to make AI. So epsilon ijk is a usual Levi-Civita tensor, and ijk here run from 1 to 3. And here there's a sum over j and k. And then we also define mi when you set the second index of m equal to 4. So we have three guys here and 3 guys here to get you the 6 generators of SO4. And you can easily see that the commutator of 2a.
Rafael, I'm the only one not listening, or?
Me too. I can't. I think it dropped.
Me neither.
It's like that, yes.
Fine. Let me write a message.
Yeah, I think, yeah, he turned it off. I think probably his internet is gone.
Okay, maybe he'll come back.
It's the snowy background he was showing us. It's frozen his internet.
Guess I'll just have to wait.
And is it storm season in Miami?
That's
Because we've lost both of his feeds in. He was logged in twice.
Okay, sorry about that.
excellent.
Welcome back.
Welcome back.
Recording in progress.
Okay, sorry about that.
No problem.
Oh. Okay, yeah, sorry everyone. Yeah, internet is not very good here. Okay, so so I was trying to motivate this factorization identity, which we use to solve the model, that is to determine the eigenvectors and eigenvalues of the transfer matrix. And I was about to get to the punchline. So so we're looking at the SO4 Lie algebra, and we had these generators M, which we split up into A's and B's, and they look almost like SU2s, but not quite. But if you now define X to be the sum of the A's and B's and the Y to be the difference of the A's and B's, then you can see that the X is close to an SU2, the Y is also close to an SU2, and the X and the Y's commute with each other. So this shows you that that indeed the SO4 can be written as two copies of SU2. Okay, so so this is a well-known fact. So maybe it won't be too surprising then if you look at, excuse me, at the R matrix for SO4. It's given by the tensor product of two copies of the SU2R matrix, and that's true. Written in a slightly fancier way, we could say that R for the D2R matrix is equal to tensor product of two copies of R for the R matrix for A1. But let me emphasize that this is for the case for rational R matrices, and this was known already for a long time. What's even better, I think quite remarkable, is that the R matrix for the twisted D2, which is the one that's in play here, is equal to the tensor product of two copies of the A11 R matrix. So now we're talking about the twisted trigonometric R matrix, the one that we're looking at here. And this remarkable fact was given in this other nice paper by Jacobson, Solor, Robertson in 2020, as well as Pawelski. Okay, and this is going to turn out to be the key tool that we use to solve the model. So let me try to make this relation a little bit more precise. So to understand the precise relation here, let's step back and go back to basics. So as all of you know, given an R matrix, in an R matrix, so at each site, say you have a vector space V, so the R matrix maps a tensor product of two copies of V to another two copies of V. And of course, we can represent the R matrix graphically as the crossing of a pair of lines corresponding to each of these vector spaces. And of course, it satisfies a relation in the pillow that that Paul showed us earlier. Then we can build another R matrix on the tensor product space. So what that means is that we can take, and now come the Blackboard fonts. So this R Blackboard is given by a product of 4 R matrices, which is taking this tensor product of 2 vector spaces and then times itself. Okay, so altogether 4 copies of V into 4 copies of V. And the nicest way to think about it is graphically. So this guy here, we can represent as now as a crossing of 4 pairs of lines. And then you'll notice, of course, that they meet 4 times, right? And that's exactly these 4 copies of R. And so, and then these Blackboard R's, they satisfy this Yang-Baxter equation. Now, actually, we'll need a generalization of this construction. So, because we need to introduce some shifts here. So, so plus theta minus theta. And in order for this to work, if you want to do that, then you also need to introduce some guys here. So, so this is actually closer to what we need. So, right. And so the way I'll denote this graphically is by putting in these extra gadgets here at the end, which correspond to these R34s. And again, one can show that these guys satisfy the Yang-Baxter equation. So, so this is actually working for basically any R matrix which satisfies Yang-Baxter and unitarity. So for the model at hand, we're going to choose the R matrix to be the A11 R matrix, which I've written here. And again, this theta was arbitrary, but I'm going to fix it now to be I pi. And then we can take care of this R34 by introducing a matrix C, which is R I pi, and then with some permutation and some extra factor. And then this equation here becomes this one. And so this is going to be now my definition of this Blackboard R. And notice it doesn't have a tilde, so this is not quite what we need, but it's almost what we need. So what we really need is, in addition to what I already wrote here, we need a gauge transformation. So, so coming back to the R, we can make a gauge transformation, and that's going to give us the tilde that we talked about earlier. And the specific gauge transformation that's needed turns out to be this one. Okay, so so with that, then you can make, so that's going to be finally what we mean by this R, Blackboard R tilde. And what's remarkable is that this guy is exactly the D22 R matrix that you can look up in Jimbo's paper.
Can I ask
So
a
this
question?
is, yes.
Sorry, hello everybody, hello Rafael.
Hi, Hubert.
I'm always confused in this problem by symmetries. So we started with something that had morally at least a UQ SU2 times UQ SU2 symmetry, I guess. When we had the A1 times A1.
Mm-hmm.
And in the end, this D22, I think you showed us has UQ B1 symmetry. Am I correct?
Yes, which is the same. It's the same as A1. Yes.
So
And you're
we've
asking,
lost, yeah. What happened to the other symmetry?
yeah. Offhand, I don't know. I should think.
It's a big problem when you think of the continuum limit, to get a little bit ahead of the talk, probably. But the D22 model somehow should have an SU2 times SU2 symmetry, but the expected conformal theory does not. In fact, it's a very different kind of model. It has at best a single SU2 symmetry. There's a symmetry that disappears. And I wonder if your procedure can tell us what's going on. But okay,
yeah. Well, what I can say for sure is that the spin chain doesn't have it, because
I know.
You can see from the symmetries, and we'll talk about a little bit at the end about the degeneracies of the problem. They're explained by basically just a single copy of this SU2 plus some discrete symmetry.
Yeah,
so,
times a Z2 or something. I know.
Exactly. So it's not there, but you want to know how it disappears.
Yeah, I want to know where it went under the carpet exactly. Where's the carpet? But okay.
Yeah.
Anyway, we can discuss this later.
Yeah, no, thanks for the question. I'll think about it, but offhand, I can't say.
Sure.
Okay.
Sorry, can I ask also a question?
Sure.
So what is the physics of this this gauge transformation? I presume it leaves the spectrum unchanged?
Sorry, the internet's not very good. I couldn't quite catch your question.
What is the physics of the gauge transformation? Does it change the spectrum? It doesn't, I assume.
Yeah, it shouldn't, right? A gauge transformation, I don't think changes the eigenvalues, but I wanted it to be the same as we wanted it to be the same as Jimbo, and you need that to match with Jimbo.
So it's a sort of an aesthetic thing. You're just putting it in a form that's recognizable.
Yeah, as far as I think so. I mean, okay. I don't think there's anything deeper. I could be mistaken, but offhand, that's what I would say.
Okay, thanks.
Yeah. Okay, so we have this very cool way to write the D22R matrix in terms of and this is what we'll call the factorization identity for the R matrix. And so the basic idea then is to use this factorization identity for the R matrix to derive an exact factorization identity now for the full transfer matrix. This thing I called it in the beginning, this T tilde of U. So it's a long calculation. I'll spare you all the details, but remarkably, the final result is very simple. I think it's quite nice. So basically, let's define a T without a tilde, which is just by sort of undoing this gauge transformation. So this T here basically corresponds to the transfer matrix you build with this R without the tilde. And the statement is that this T now, blackboard T, is given by a product of two ordinary T's. So this is T of U, and then another T it's just shifted by I pi. And this guy here is just a scalar factor, a very simple overall scalar factor, which I've written here. So basically, it's just given by a product of two T's with a shift, U plus I pi. And that's exact. It's true for any finite value of the length of the chain. So that's really the main take-home message, that such an identity exists. Let me just add a few more details. So as I said, that this guy here is just the Skleanian transfer matrix, almost Skleanian transfer matrix for the A11 R matrix. Okay, so it has some, but the K matrices are kind of trivial, right? here you would have a K minus, a K right, say, or left, one of those, but here it's identity. So it's identity here, and the other guy here is just an M. And so this is the transfer matrix built from A11. And also careful that the monodromy matrix that we use here, instead of being for n sites, now is doubled, right? So it's 2 n sites. And furthermore, it has IPi inhomogeneity at alternate sites. And that comes from the fact, if you remember, that this guy here is built from 4 copies of R, but there's these shifts, right, by theta. There's a shift by theta here, plus theta minus theta, and here theta is IPi. And so that gives rise to these bulk inhomogeneities at alternating sites. And then, so since this is A11, we know, all of us know how to use algebraic beta ansatz to obtain the eigenvectors of this T of U. And then, and since these guys commute, then these are also going to be eigenvectors of the guy that we didn't know, this blackboard T. So now the problem becomes quite straightforward. But let me emphasize one more thing. If you were looking carefully, so this is not quite what Sklianin wrote, even for the special cases of the K matrices. There's also this funny shift here by IPi. And so this we'll call a boundary inhomogeneity. And it turns out to play a significant role in this business. So just for completeness, let me remind you how this goes. So when you want to do the algebraic beta ansatz, you define some creation-like operators here, and you act on the reference state. Remember, we have 2 n sites now, and we'll call that this beta state. And then, and so well, actually, you need this gauge transformation. So together with the gauge transformation, these are going to be eigenvectors of the transfer matrix we're interested in with these eigenvalues, lambda. And we can read those off. Again, from this factorization identity, is just the product of the eigenvalues of this ordinary T of U, the A11 transfer matrix, again, up to this simple overall scalar factor, phi. And then these chi's we know from algebraic beta ansatz, and it's given in this formula here. Details are not so important, where Q is the Q function, which I've written here. So the zeros of the Q function are exactly these beta roots appearing here. And of course, we know that that these beta states are going to be eigenstates of the transfer matrix, provided that that the beta these U's satisfy the beta equations, which I've written here. And these are and let me emphasize that it's not a typo here. While you have sinh here, as you'd expect, what you have here are coches instead of sinches. And you can trace back the origin of these coches to the fact that we had this boundary inhomogeneity in the transfer matrix for this T, right? This T of U had this not quite Sklianin transfer matrix. It had this boundary inhomogeneity. And these are the beta equations that were conjectured by Robertson, Jacobson, Salur, and so this provides a proof. Okay, so there's a few bonus results that now we can get without any effort. So the first thing is that we can now understand the degeneracies in the spectrum of this model. So this is related to the comment that Hubert made a few minutes ago. So on the basis of quantum group symmetry alone, and now just for simplicity, let's focus on the case of real anisotropy, we expect that the degeneracies of the transfer matrix should be given by the Clebsch-Gordon theorem. So you remember I said that at each site you have a four-dimensional vector space, but it turns out that that four-dimensional vector space decomposes under this quantum group into a triplet and a singlet. So that's for one site. So if you have now two sites, you'd expect that it should just be given by Clebsch-Gordon theorem, and so you'd have singlets, triplets, and quintuplets, and in fact you have two of these and three of these. That's what you'd expect, and similarly, say for three sites, then you should make threefold tensor product, and again by Clebsch-Gordon, this is what you would expect. But this is not what you see. What you see is actually, and let me emphasize that the numbers that appear here, right, are always odd. These are all odd numbers, so we have only odd degeneracies. But in fact, what you see is a lot more interesting. The observed degeneracies, and you can just do it on your computer, is now you start to see some even degeneracies, like you get this 6 here, in the case of two sites. And in the case of three sites, you get a 10, and you get the 6, and you get a 2. Okay, so as well, so we have also even degeneracies. And if you stare at this, you can begin to understand maybe where they come from, right? Because what happens is that two of these threes become a 6. So the two triplets become degenerate, they become a 6. And here, say, two of these 5s become degenerate, actually 10, and then another pair of 5s gives another 10, and so on. So it suggests that it's due to some kind of discrete symmetry, and that's in fact so. There's a Z2 symmetry. And again, as these folks pointed out, there's this operator, this blackboard C, which is in fact given by tensor product of the ordinary C's, which I showed you back in the beginning. This commutes with this transfer matrix, this blackboard one. And now, but what you can now say further is that is the action of this guy on the raising operator, this creation operator B from the boundary and Baxter algebra. And what it does very nicely, it shifts the argument by I pi. So, so that means that if you would take this C operator and act on a beta state, it just shifts all the beta roots by I pi. Right? U1 gets I pi, and then UN goes to I pi. Same for all of them, because of this simple fact. And so, if I have a solution of the beta equation, say U1 to UM, then we have either one of two possibilities. Either the Q function, so let me remind you, the Q function is defined like this, which depends on the beta roots. So, so either when I shift the argument by I pi, either I get Q or I don't get Q. That's obviously true. But now with a little thought, you can convince yourself that in the first case, if Q is invariant under shifts of I pi, then the beta state is going to be an eigenstate of C, and therefore, and is also a highest weight of the quantum group, and therefore it's going to lead to odd degeneracy. So like some of the guys here, the ones with degeneracy. On the other hand, if Q is not invariant and under shift by I pi, then the beta states that correspond to Q of U plus I pi and Q of U, they're mapped into each other by this transformation C. And therefore, it'll lead to these states here with even degeneracy. And so now we have a quite precise control on these on the degeneracies in the spectrum. So that was one kind of bonus result. Another one is this, we can come back now to this boundary and homogeneity that we saw appearing. So we saw it appear here in a very special context, but in fact, this is something quite general. So we can put some generic boundary and homogeneity, U naught, in Scalianan transform matrix, and put in some RK matrix here and some left K matrix here. And this leads to an integrable model. So again, here we have a boundary and homogeneity. Note that, say this guy here, this K matrix, which now has a bar, it doesn't satisfy the usual boundary and Baxter. It obeys slightly generalized because now this boundary homogeneity appears here. By the way, I should probably have drawn the picture. So what's going on with this K matrix is that somehow that particle comes in, but with some rapidity U, but then the angle though is no longer U when it reflects, but it's something like U plus U naught, something like that. So so you can also think of this as some kind of moving boundary, which is giving some rapidity to the particle when it reflects. And so, but this is not a big deal. You can always map this K bar matrix to the one without the inhomogeneity by this simple transformation. And again, we can basically repeat all of Scalianan's argument to show that this transform matrix again commutes for different values of the spectral parameters, so it leads to an integrable model. But even and this has a profound effect on the beta ansatz solution. And we looked at just as an example, the case of the twisted A's, and we took the boundary and homogeneity to be again I pi, just as in the A11 case that we were looking at before. And then what we found is that now all the Q functions are affected by this boundary and homogeneity. So so without the boundary and homogeneity, the Q functions would be sinh, okay? But because of the boundary and homogeneity, now you get Cauchys here. And again, it's true for all the Q functions, L running from 1 to n. And again, it can all be traced back to this. Okay, so let me conclude. So what we showed here is that just the good old-fashioned algebraic beta ansatz can be used to solve this D22 quantum group invariant open chain. But that relied on a miracle that that this D22R matrix can be factorized into product of A11R matrices, where the problem becomes very easy. So, which led to, as I said, an exact factorization identity for the transfer matrix. But how about now for, so this was the case of D22, how about the higher twisted D matrices? What can we say about those when n is bigger than 1? Well, unfortunately, this fantastic miracle is no longer available. But now that we know the idea how we were able to solve what the answer looked like for D22, then we can now use analytical beta ansatz to solve this model, and well, that part seems to be working. We can't prove it, but we have a conjecture, and that can be checked numerically. But the most interesting question is whether those models also have are described by non-compact CFTs in the continuum limit. And well, that's still a work in progress. And I hope we'll be able to make some progress on that. But that's it for today. So thank you very much for your attention.
Okay, let's think about. Are there any questions?
I have a question and a comment. So the comment is the model was discovered, in fact, by focusing on the antiferromagnetic Potts model, which Baxter showed that criticality is equivalent to a staggered 6-vertex model whose transfer matrix is written in the form T of U plus I pi. So I think your factorization identity has a lot to do with this original construction. The way we got to D22 was really starting with a factorized model and then kind of combining the weights, combining the contributions of the Boltzmann weights to realize that it had to do with D22. And I think your factorization identity is somehow undoing this. Now, we had done it only in the bulk, not on the boundary. I think what's great is you're doing it at the boundary as well. But I think this is worth investigating a little more. I think this is really the same thing. Anyway, that was my comment. The question has to do with the operation of shifting U into U plus I pi, the spectral parameter. Do you have any idea what the macroscopic operator realizing this might be? You know, something expressed in terms of the microscopic spins directly at the level of the Hamiltonian? Is there a way to reconstruct it by inverse scattering, for instance? I mean, it's a very interesting question.
So I didn't quite catch the question.
Well, we know that we can take a solution of the beta ansatz and shift all the spectral parameters by I pi and get another solution of the beta ansatz with the same eigenvalue. Now, this operation of shifting the U's by I pi, could it be expressed in local terms as the action of some operator that depends on the spins?
Well, it was, isn't it this,
Is it complex conjugation, essentially?
Isn't it this C? 1 second. So, isn't it this, are you talking about this?
Yeah.
So you want to write, so you want to understand this C, or as?
I forgot a little bit, honestly, but C, remind me what C was.
Yeah, so basically, you remember this, the C without the boldface you introduced, I don't know, 30 years ago. And this, I think it's just like this.
Yeah.
Right, so C is basically, I forgot, but it's like permutation times R by pi. So that's your C, and then this Blackboard C is just this, I guess two n copies of this C, and so we prove it's obvious that acting on a beta state, it just shifts all the rapidities by pi.
Yeah, okay. I realize I forgot a little bit, but I was thinking of the continuum limit. This operation of shift exchanging U and U plus I pi has something to do with changing the SZ component, I think, of the U1 in the SL2R over U1. Okay, anyway, forget it. I'm looking for ways to connect to the continuum limit. You know, this is very mysterious, with the appearance of the black hole sigma model, and we still don't understand why there's a quotient by U1, and we still don't understand why there's an emergence of non-compact degrees of freedom. Anyway, I keep looking for this, but obviously it's not going to be today that we are.
But Hubert, just one question though, because you made a comment and I'm not sure if I agree or not, but so this is the action of C on this blackboard T, but acting on the single T, I think what it does is it shifts U by I pi. So so I think so. This shows that T and the one shifted by a pi, they're related by a unitary transformation, but same spectrum. But I don't think it's true necessarily that it's the same eigenvalue, right? I think they can be different eigenvalues. So, right. So what I know is that if this is an eigenvalue chi, then this is also an eigenvalue, but they're not necessarily the same. And I think it's tied together with this degeneracies.
Yeah, probably.
Okay. And also going back to your remark, indeed, when we prove this this factorization identity for the transfer matrix, there should be a faster way to go. Yeah. So
Yes.
So right. So we use this, but as you remark, we also needed something like this for the K matrix, which I didn't talk about. But indeed, this was essential to get this. And well, you can. It's in the paper, but indeed, you need some kind. It's more messy than this.
Sure.
But in fact, you do need some kind of factorization. Otherwise, you don't get this.
Yeah, I think
So
in the case of periodic boundary conditions, it's probably easier to see. I think so.
Yeah.
Okay.
Exactly. Good.
Okay.
Good to see you, Ben.
Yeah, you bet.
Yeah.
Are there any more questions? Okay. So let's thank Rafael again.
Okay. Thank you, Anna.
Okay, so thank you, everybody. And we come back tomorrow at the same time.
Okay.